with Milton and Hovsepyan. Actually, we started this project with Milton when I was a postdoc in Utah, University of Utah, some years ago. So one might think, when looking at the title, where is the material, right? This is not related to the title of the workshop, but this is in fact, it is implicit. I will show you a little bit about this. So let's start. Let me recall the classical convexity conditions in the calculus of variations. We know there are 4 of them. So in the top we see the famous convexity condition, right? Yeah, by the way, today I noticed a couple of typos in the slides, and I apologize for that. I will let you know when there is a typo. So here in the quasi-convexity condition, this set, for instance, has to be bounded. Okay, this is so the famous convexity condition, and then the quasi-convexity condition, and we know that quasi-convexity comes from is equivalent under some growth conditions, and with a little bit of some minimal regularity conditions on f, if also it depends on x and the function, right? Then this quasi-convexity is equivalent to lower semi-continuity in the with respect to the weak W1D convergence. And then here we have the rank 1 convexity, which is of course the same inequality as for convexity, but the matrices have the difference is rank 1 or 0. And we know that convexity implies quasi-convexity, and this implies rank 1 convexity. And there is the 4th condition that we know also, which is the polyconvexity condition. So function is polyconvex if it is basically a convex function of the minors, and this C is by a matrix. There is another little typo here. This mi, there should be a different index mk. Okay, so these are not the same I. So of course we have a bunch of minors. If you have an m by n matrix, it has a bunch of minors. R is much larger. Then we know that polyconvexity is in between quasi-convexity and convexity. This is a consequence of the fact that determinants are now Lagrangians for the gradient problem. So okay, now we are interested in quadratic forms, and there is a lot known about quadratic forms, quasi-convex quadratic forms. In particular, it is known that in the case when f is a quadratic form, then rank 1 convexity and quasi-convexity coincide, they are the same. And the condition, so this was proven by von Hove, and the condition reduces to the rank 1 convexity condition for a quadratic form reduces to this inequality. You just plug in a rank 1 matrix, the result is a non-negative biquadratic form. Okay, what about polyconvexity? And polyconvexity is explicitly characterized for quadratic forms, and the characterization is the quadratic form is polyconvex if it is the sum of a convex form plus a linear combination of the 2 by 2 minors. It is also known that when one of the dimensions is 2, then quasi-convexity also implies polyconvexity. Basically, they are the same.
And the result has been proved before the definition of quasi-convexity.
Yes, long ago. Yes, before, like 15 years before yes, like 12, 13 years before the definition of quasi-convexity. Because this is also related to the so this is, people studied this in convex geometry, and they call these positive forms and totally positive forms, etc. I will tell you a little bit about this. Yes, so in the case and one of the dimensions is 2, positive form is a totally positive form, by quadratic form in their language, in the language of real geometry or convex geometry. And this is also related to the problem of sum of squares. Okay, so and also when it was known long ago that when both dimensions are larger than 2, then there exists a quadratic form that is quasi-convex but not polyconvex. It was proven in 1928. There was no explicit example given, but the existence was proven. Okay, so this means basically that this means that polyconvex forms are generated by squares of linear forms and null Lagrangians, and this means that quasi-convex forms are not. In fact, one can prove, it is not difficult to prove that, okay, maybe I can tell you, okay. So it is not difficult to prove that if you look at the n by n quasi-convex forms, at the set of n by n quasi-convex forms, it's a convex cone. And it has a Krein-Milman property and a really simplified version. So every quasi-convex quadratic form can be written as just one extreme ray plus convex form, okay, plus polyconvex form. So polyconvex plus exactly one extreme ray. And for example, in the case of polyconvex forms, or 0 extreme ray that is not polyconvex plus polyconvex form, 1 or 0. Okay. Okay. So this is quite interesting. That I learned about this 4 years ago, a couple of years ago. So in the calculus of variation literature, we know that this example appears as the first example that is quasi-convex but not polyconvex, right? But it turns out that there was an example given in this convex geometry community like 6 years before that. Okay, so this was pointed out to me by a reviewer of one of my papers. I presume that the reviewer was from the convex geometry community, and he told me you should read choice papers, and he pointed out a bunch of papers that I had a look at, and it turns out that, okay, this example was given before. Okay, so this is...
it's nicer, right?
Yeah, this is nice. Yes, nicer.
Symmetric.
Yes, in fact, you can take also the other... so this part only depends on the diagonal elements. And then you have 1, 2, 2, 3, then there is this cycle. You can take the other cycle, doesn't matter. You also get a quasi-convex form. Okay. But if you mix, you get a convex form. You need to take just one cycle. Okay, so let's denote by CNN the set of all quasi-convex quadratic forms. Yeah, quasi-convex is missing here. Quasi-convex quadratic forms n by n, and this is a convex cone. And yeah, so M is a symmetric M is a fourth order tensor or a symmetric matrix, which is the size of n times n. So Milton defined the so-called weak extremals. Weak extremals are SOF is a quasi-convex quadratic form called a weak extremal if one cannot subtract the convex form from it while preserving the quasi-convexity of the form. It is minimal in that way. You cannot separate the square from it anymore. And the questions, so he introduced this definition because he realized that, Milton realized that these weak extremals are important, can play an important role in the theory of composite materials, Actually, by using them, you can one can generate new bounds on the effective properties of composites. And, there were then several questions then that one would like to study. So we will call this. So these are weak extremals when you cannot separate a perfect square, and the extreme rays we will call them strong extremals. Okay, that are not separable at all. Let's call them strong extremals. And general question is whether these are the same. Weak extremals and strong extremals are the same in any dimensions. And another question is, I think in higher dimensions this is almost obvious, but in 3 by 3 it is not obvious. It is not straightforward at all. I will show you. And the main goal would be the large goal. Big goal would be characterize all 3 by 3 at least quasi-convex extremals. So as I told you, if you characterize strong extremals, then there is the Krein-Milman property telling you that anything that is not polyconvex, but that is quasi-convex but not polyconvex, is exactly one extremal plus something polyconvex. Okay. So why extremals? As I told you, one can use these extremals to generate new bounds in the theory of composites. Like so, the famous the approach of using just non-Lagrangians is known as is very well known, and one wants more, and these are the ones that one should use, the strong extremals or the weak extremals. We will see if they are they are the same or not. And also, I think they are interesting just in the calculus of variation community. So from the perspective of quasi-convex analysis. Okay, so in order to study them, we have the condition, rank 1 convexity or quasi-convexity condition, right? F is a quadratic form. It's a quasi-convex if and only if you plug in a rank 1 matrix, it's non-negative. The resulting quadratic form is non-negative. So we can separate, of course, we can separate the x and y variables, and the negativity means it's a biquadratic form, but it's separable. X has a degree 2 and y has a degree 2 in it, and so we can separate the x and y variables by writing it in this way, and this S is called the acoustic tensor, or we will call it the y matrix. So this will be non-negative for all x and y vectors if this matrix is positive semi-definite for all y vectors, right? Okay. So we wanted to study them to generate new. When we started this project, basically we didn't know the Choi-Lam example, and we only knew some examples from the calculus of variation literature, and none of them was an extremal. Okay, so the Serre example is quasi-convex but not polyconvex, but it is not an extremal. Even if you take the maximum epsilon, right, or it may not exist even, it may not become an extremal because it is not clear. I think it's with high probability it will not be extremal if you take the biggest extremal. So we took the standard, the naive approach to start with the forms with most symmetries. So first we were looking for extremals in the set of quadratic forms where so this is the tensor, the form for the tensor. I was using M, now it is so the form for the tensor when it has a cubic symmetry, linear elastic cubic symmetry. Then we found that these don't generate anything new. Okay, if you have a quasi. So cubic symmetric, linear elastic cubic symmetric basically is the tensor depends only on it has only 3 independent parameters, and it is quite simple, but if it is quasi-convex, it is not obvious that it has to be polyconvex. The form is not something like diagonal or something. It's not at all obvious, but it is straightforward. They don't generate anything new. So then so after considering different examples and thinking about this, we came to a conclusion that you may want to look at the determinant. Okay, you may want to look at the determinant and the determinant of this matrix. Okay, of this matrix S. Why? Because of this simple reason that so we want to understand if something is an extremal or not, strong extremal or not. Strong extremal means it is not separable, right? If you are separated into 2 non-negative parts, then they have to be linearly dependent. Only this is the only way. So if you are able to separate, then also the Y matrices separate. And the determinant, imagine you separate the B matrix from the A matrix. In that way you separate, then the determinant of A has to be larger or equal than the determinant of B, right? So this means that if you want to prove something is an extremal, then the determinant may be, you look at the determinant, if the determinant is not separable, right, then you may be able to prove that the form is itself not separable. But it is not that straightforward, because the determinant may be non-separable, but right, so the determinant, imagine the determinant is an extremal polynomial. It is non-negative, 6th order homogeneous polynomial in the Y variable, and it is non-separable means still you can separate it in 2 parts, right, like a convex combination of the same thing. And then you will have another matrix B that may have the same determinant, right? You don't know. So it may be that another matrix B also has the same, like alpha times the determinant of A, and so it is not straightforward that if the determinant is not separable, then the form is not separable, but this is some approach that we took, and let me show. So the question was whether the determinant would tell about the form. Okay. There is enough rigidity in the determinant or not, which is if the determinant is non-separable, if the form is, then whether this implies that the form is non-separable or not, and very surprisingly the answer was yes. Okay. So let me show you. If you look at the Choi-Lam example, and funnily enough, we discovered with Milton this example because we didn't know about that during our work, and this appears in one of our papers. Of course, we didn't know, right? This is in 2015, I think. This was. So if you look at that example, and also we got a lot of insight from this example. When we discovered this example, we got the insight from there too. So if you look at the determinant, this is a famous polynomial in the community of convex geometry, and this is very well known to be an extremal polynomial, 6-degree homogeneous polynomial that is an extreme ray of the cone of that polynomials. And so this is an extremal polynomial, and this is an extreme ray. So then we thought maybe the characteristic feature might be that the determinant of an extremal form has to be an extremal polynomial. Okay, now this is the question, whether they are equivalent. And if they are, then this is a quite significant reduction of the problem, because you have here we have 2D variables, right? 2D variables. and then the problem reduces to just d variables. To the problem of d variables, you just look at the determinant. Okay, then, so we were indeed able to prove that in the next symmetry class, so we assumed orthotropic symmetry, and we assumed that, we assumed orthotropic symmetry for the tensor of the quadratic form or the material, which means it is given in this, so the quadratic form has this form, basically some form that depends only on the diagonal elements plus so these squares. So orthotropic symmetry. Then we were able to prove that. So we assume that these coefficients are automatically non-negative because the form is convex. But we assumed that they are positive. So if you assume they are strictly positive, then we were able to prove that if the determinant of this thing is an extremal polynomial, then the form is a weak extremal. Okay, we started with the question of weak extremals because strong extremals at that point were quite hard to attempt. So we were able to prove that, under this positivity condition in the class of orthotropic symmetric quasi-convex quadratic forms, so with 3 by 3, then the extremality of the determinant implies weak extremality of the form. Weak extremality, again, let me remind you, is that you cannot separate the perfect square. Okay, then it turned out that these 4 cases are qualitatively different. So we separate the following 4 cases. Case 1 is when the determinant, now we will be in 3 dimensions, 3 by 3 for a while now. The first case is when the determinant is an extremal polynomial that is not a perfect square. Okay, as you remember, for the Choy-Lam example, it was something and it was definitely not a perfect square. For example, if you take like the sum of the squares of the diagonal elements C1, 1, 2, 2, and 3, 3, the determinant will be an extremal polynomial, y1 square, y2 square, y3 square, but it will be a perfect square. So, for the Choy-Lam example, it is not a perfect square. Then the second case is when the determinant is identically 0. Identically 0 is also an extremal, but and it's a perfect square, and it is 0. Right? 0 is perfect square both and is an extremal. And then case 3 is when the determinant is a perfect square. In fact, it is quite straightforward that because it's a perfect square of a third order homogeneous polynomial, it has to be an extremal. Okay, any perfect square of a third order, it has to be an extremal. It's quite straightforward. So the determinant is a perfect square and is not an extremal at all. Let me show you what we got. So in case 1, we were able to prove in 3D that so if the determinant is an extremal polynomial that is not a perfect square, case 1, then the form is as a weak extremal. So the determinant is quite rigid. This shows the rigidity of the determinant. So if it is not separable, then the form, you cannot separate a perfect square from the form. In case 2, we were able to prove that if the determinant is, case 2 is identically 0, this is in fact a strong algebraic condition, and I was believing, we were able to prove that either the form is weak extremal or polyconvex, but I was believing it has to be polyconvex. This is quite strong algebraic condition. It's identically 0 for all y, and we eventually got it. I will show you. So case 3, it's a perfect square. We were able to prove with Milton that it's either a weak extremal, polyconvex, or has to have this form, weak extremal plus a linear form squared, when this weak extremal has a 0 determinant, identically 0 determinant. Okay, then recently we attempt the strong extremals with Hovsepyan. And let me show you what we got. Okay, so I tried again the class of orthotropic symmetry, the class of forms that have orthotropic symmetry, and I was able to prove that in that class again, if the determinant is here, you don't even, because of the form, this has quite a specific form, you don't even need the determinant to be non-zero or perfect square. It cannot be perfect square. So if it's an extremal polynomial, then the form is an extreme ray of that coin, in the strong sense. Then, so these are the results with Hovsepyan. We were able to prove that the determinant is rigid in the strong sense, even in the strong sense that, so this is the previous result. We got a weak extremal. We were able to prove that in case 1, when the determinant is a extremal polynomial that is not a perfect square, then the form is an extreme ray. Has to be an extreme ray. So the determinant is very rigid. So for the Choi-Lam example, as I showed you, this is the example. The determinant is this, and it's indeed extreme ray. Extremal polynomial, 6th order homogeneous extremal polynomial. What did we get in case 2? As I told you before, we had either weak extremal or polyconvex, but then we were able to prove it has to be polyconvex. So if the determinant is identically 0, the form is basically, when you plug in a rank 1 matrix, it's a sum of squares. And it can be maximal number, it can even be a sum of maximal number of squares. So there is no restriction there. We have an example when it's a sum of maximal number of squares, still the determinant is 0. Just simple example is square something plus something else squared, the determinant is 0, obviously. And it's polyconvex. In case 3, so before we had case 3 is when it's a perfect square. Before we had weak extremals, either it's a weak extremal or polyconvex or has this form, weak extremal plus linear form squared, and this has an identically 0 determinant. And now we have it's either an extreme ray or it has to be either an extreme ray or polyconvex. So in these two cases, in this, so in the first case, this is the optimal result because you cannot prove better, right? So it's an extreme ray. And this example shows that you cannot prove better, and that's it. So also this, in this case, this is the optimal result. It's polyconvex because when you plug in a rank 1 convex matrix inside F, it doesn't matter whether it was convex or polyconvex. Same thing, the null Lagrangians disappear, right? You only see the convex part. So the plugging in a rank 1 matrix, this is how you check whether it's quasi-convex. You don't see the null Lagrangians, they disappear. So this is, again, optimal. This is the best you can hope to prove, but this we don't know. So when it's a perfect square, we have an extreme ray or polyconvex. I believe that one can rule this out, but we don't know. We don't have a proof. It has to be a polyconvex. But okay, yeah. So we believe it probably should be polyconvex. An example would be like this. For example, you take the squares of the diagonal elements. The determinant is this. It's a perfect square. It's an extremal. Okay, what about the case 4? Case 4 was when the determinant is not an extremal. We had a conjecture with Milton that then the form is not an extremal. Basically, this is necessary and sufficient, but Bleckerman, Raita, Shankar, and Zing proved recently that actually there exists a form, and this form was given by Buckley and Sivich. They proved that this form was given by Buckley and Sivich. Buckley and Sivich mentioned that this is an extremal ray, and they have a class of, so they generate a class of extremals depending on two parameters, and this comes out when you give specific values to these two parameters. And so it was known that this is an extremal quasi-convex quadratic form, and Bleckerman, Reiter, Shankar, and Zinn proved that in fact this is a counterexample to that claim, that so this is an extremal, but the determinant is not an extremal polynomial. Okay, so this looks quite complex. And they also proved that in the case, as I said, we had another conjecture with Milton, that so it's quite rigid. In the case, in 3 dimensions, it's quite rigid, and weak and strong extremals have to be the same. And they proved that conjecture. So in 3D, if you have a weak extremal, it has to be a strong extremal. What about higher dimensions? We have a result in higher dimensions with Milton is this. So assume now we are in dimensions higher or higher than 3, and the determinant is a non-zero irreducible extremal polynomial. We don't require it to be not to be a perfect square, but to be irreducible. Okay, this is important. In fact, in 3D, 6th-order homogeneous polynomial that is non-negative, if it is reducible, it has to be a perfect square in 3D. So these are equivalent. In 3D, irreducibility and not being a perfect square are equivalent. It turns out that in higher, so if you have to require in some sense, this example shows that you have to require irreducibility to hope to prove something. For example, so we prove that if the determinant is a non-zero irreducible extremal polynomial, then the form is a weak extremal. So it's again, it is quite rigid in any dimensions, but not as rigid than in 3 dimensions. In 3 dimensions, even weak and strong are the same. And this example shows that you have to require irreducibility, because you take the Choi-Lam form, right? This is the Choi-Lam form, and add the additional diagonal term. For example, in 4D, if you are in ND, just add the remaining diagonal elements. Then the determinant is this. It is reducible, right? It is still an extremal, because it's extremal times extremal, and simple. This one is just one summand, right? Monomial times an extremal is an extremal. But it is reducible, and this, as you see, is not a weak extremal, because this is non-negative as a quasi. This is quasi-convex, and you can separate this perfect square. So let me show you the key ingredient in the proof of case 1, for instance, when you want to prove that the determinant is an extremal polynomial, you want to prove that the form is also an extremal quasi-convex quadratic form in 3D. So assume that if you assume in contradiction that you can, it is not an extremal, you can separate the Q1 from it. That is, assume we can separate the Q1 from it, and we want to prove that this Q1 has to be a scalar multiple of Q, using the fact that the determinant of Q is an extremal polynomial that is not a perfect square. Then we write in the standard form. So a key idea is to consider this polynomial, to consider the polynomial. So S, the matrix of Q minus lambda times the matrix of Y. So this depends of course on lambda and Y. And it can be written simple calculation like this. So determinant of S minus this sum of lambda times the first order coefficients, second order, third order coefficient would be the determinant of S1. It turns out that these coefficients are ordered. These coefficients are ordered that we prove in this lemma. So this lemma basically says the following. Assume you have two symmetric matrices, positive semi-definite, ordered two symmetric matrices. A is larger or equal than B in the sense of quadratic forms. Then you consider this kind of sum. So fix integer m that is between 1 and n, and take, so sum over all mth order minors of B times the cofactor, but you take the cofactor of A, corresponding cofactor in the matrix A, not in B. If you take the cofactor in the matrix B, then we know you get the determinant of B. But instead, you take the cofactor in the matrix A and you multiply them, you sum. So it turns out that so for a smaller index, you get a bigger sum, and you normalize by the number of sums, of course. So it turns out that you get a larger sum when you take the cofactor in the larger matrix. Right, so assume this. So when you take, so you take a small minor. You take the smaller minor in the small matrix. Okay, in the smaller matrix, multiply by the cofactor in the larger matrix for a smaller index. So this is increasing. In fact, so this decreases. Right. So this means that these coefficients are ordered. They are basically in between determinant of S1 and determinant of S. But because this determinant of S is extremal polynomial, in fact, this determinant of S1 is between 0 and determinant of S, and it has to be a positive multiple of the determinant of S, because determinant of S is an extremal polynomial, and the same have to do these two, because they are in between. This is ordered. So taking that into account, you get that this polynomial is actually separable. It's a polynomial in lambda times the determinant of S. And this polynomial in lambda has real roots, because so what is the polynomial? It is this minus this. You can write this as something times the determinant, something times the characteristic polynomial of a symmetric matrix, right? So it is quite easy. This is the determinant of S. You introduce the 1/2 power, you get this is the determinant of S times the characteristic polynomial of a symmetric matrix, so the roots are real. The roots are real and they are larger or equal than 1. If these are the roots, then we consider this Q minus lambda, the smaller. We pick the smallest root and we consider this difference, and then we prove that this has to be identically 0. In fact, this Q1 is 1 over lambda 1 times Q. Okay, so how do we prove it? This has an identically 0 determinant, right? Because the determinant of this thing is the y determinant is phi lambda times the determinant. So if lambda is 1 is the root, this has a 0 determinant, identically 0 determinant. And if we are also able to prove, so next we prove that the goal is to prove that this is non-negative. This is quasi-convex. Okay, we prove that first prove that this is quasi-convex, and because this is quasi-convex and it has identically 0 determinant, we go back to the theorem we have. It has to be polyconvex. Because this is polyconvex, you write Q as lambda 1 times Q1 plus polyconvex thing. But the polyconvex thing will involve a perfect square, is square, right? At least one square. But if it's this times this plus squares, it means that it's not a weak extremal. You can separate a square. And we get a contradiction. We already know that, right? We want to prove strong extremality, but we already know that we have proven with Milton it is a weak extremal. This we know, right? So that's the way to prove it, and I think this is all I wanted to say.